This is Manchen Wang, and this is my lab report for Physics Lab 3. Here is my table of content. Here is the introduction of the lab report. The purpose of the lab is to practice and combine Newton's second law and the universal gravitational force. We used the two computational models to create and compute the interesting black hole and spaceship model. And here are the lab results. We gained the mass of the black hole from the randomly generated trajectory and gained an optimal initial velocity for the spaceship to observe the black hole. Here are the two fundamental principles we used in the experiment. So we'll first use the universal gravitational force formula to know the net force on the object. And then we'll use the position update formula, which is the Newton's second law, to update the rate of change of velocity, and then know the change of position of the object. In part 1 of the experiment, we are required to find the mass of the black hole, and with 447 data points we collected, I gained the final mass of the black hole. And here, the system is the planet, which is the one orbiting around the black hole, and the surrounding is the black hole, which applies a gravitational force to the planet to make it orbit around the black hole. Here are the codes I used for part 1 of the experiment. Here we used momentum and Newton's second law to calculate the net force applied on the planet. And then using that net force, and since the gravitational force is the only force applied on the planet, we used that to calculate the mass of the black hole using the universal gravitational force formula. And in part 2 of the experiment, we're asked to find an optimal trajectory for the spaceship to observe the black hole. And in here, the system is the spaceship or the planet based on which one we're analyzing on. And the surrounding are planet, black hole for the spaceship, and black hole and spaceship for the planet. Here are the codes I used for part 2 of the experiment. On the left, I put the time and initial velocity setting for the spaceship, and the velocity is the lowest speed to escape from the planet's gravity, but at the same time making the spaceship closest to the black hole. And I also put the time to a place where the spaceship can be the closest to the black hole. And on the right, I have the calculation for velocity update and position update for both the planet and the spaceship using Newton's second law and universal gravitational force formula. Here's the discussion part of the lab report. So the limitation of using computational model for both of the experiment parts is that the computational model are too theoretical, and it's not able to consider too many factors. And for the what does it mean discussion problem, so the net force are outside factors that determine the motion of the object. It is a measurable physics component, and the rate of change of momentum is determined by the net force on an object. It is not directly measurable. For the what-if problems, and for part 2, so in order to get into the orbit of the black hole, the spaceship still needs a relatively high speed to prevent being sucked into the hole, but the parallel component of the velocity needs to be increased and the perpendicular component needs to be decreased so that the spaceship can orbit in a relatively slow speed and while still prevent itself from being sucked into the hole. The conclusion for the experiment is as follows. We gained the mass of the black hole and the optimal initial velocity for the spaceship to briefly observe the black hole.